Hi, I'm Adam Jones, and today I'm going to talk to you about our paper Asymmetric Effects of the Ebbinghaus Illusion on Depth Judgment. This is work primarily done by my student Hunter Finney in the High Fidelity Virtual Environments Lab, or High-5 Lab, at the University of Mississippi. So first of all, a little bit about the Ebbinghaus illusion. Uh, if you've had any intro psychology class or sensation and perception class, I guarantee you've seen this illusion in a textbook. It's sometimes referred to as Titchener circles, and it's a relative size illusion. So how it works is you have a disk of a particular size surrounded by a ring or annulus of disks of different sizes. And for our first one here, you see we have a disk surrounded by larger disks. And for the second, we have the same disk surrounded by smaller disks. And for the third one, we just have the disk by itself. Now, comparing these, that central disk looks a lot smaller than C, even though they're exactly the same size. And similarly, B appears to be larger than C, even though it's exactly the same size. So this is sort of the general way this illusion works. Um, there's been a lot of work examining the effects of Ebbinghaus on reported size of objects, but also on the effects elicited, the effects it may have on action-based tasks. One of the action-based tasks that's typically been used for studying Ebbinghaus is grasp aperture. So in other words, they'll have people reach to targets that are surrounded by annuli that are either of large circles or small circles, and then measure the width of the grasp as they're going in to grab it. Turns out this actually correlates very, very well to the physical size of an object. So if you're reaching to a juice glass versus a coffee mug, your grasp aperture is going to scale accordingly. And what people have found is that though subjects report the sizes of the disks in these Ebbinghaus configurations to be either larger or smaller than they actually are, their grasp aperture doesn't reflect it. And so this has been used as evidence in the argument that visual illusions do not affect action-based tasks. In recent years, there's been a lot of debate about this, and Ebbinghaus has been a rather large part of that debate, actually. And it's also been used as evidence for the dual pathway model of vision. Now, the dual pathway model of vision, there's a lot of other evidence in addition to the fact that, a lot of evidence in addition to the studies indicating, and I wouldn't say facts, but the studies indicating that visual illusions don't typically affect action-based tasks. Now, the problem is that every study, including the one we're going to talk about today, is imperfect. And one of the problems with these studies is that reality is a problem. We're limited by what we can display and what we can do in the real world. How most of these reaching experiments have been done is you have a printout of a large or a small annulus, and then a small physical disk is placed in the center to act as that central disk. And a person then reaches for that and also verbally reports the size of the disk. Now, it's hard to control very subtle cues in the real world. In particular, if you're using a three-dimensional disk on a 2D printout, there is three-dimensionality built into that. There's stereoscopic cues, there's motion parallax cues, there's all sorts of cues involved in just this very simple experiment. Fortunately, we're not limited by necessarily all of these things in the virtual world. For instance, we can make effectively truly 2D stimuli for a person to reach to. And this is what we do in the study that we're about to talk about. We take the Ebbinghaus style sort of experiments and bring them into the virtual world. We do this in two phases. The first phase is a size matching task that takes place in the real world, and this is done to effectively establish that the stimuli that we chose is going to elicit the effects that you would expect to see from your typical Ebbinghaus experiments. And then the second phase of the experiment is a blind reaching task that takes place in the virtual world. So blind reaching is an action-based task. You're not doing an estimate of size, saying it's X% bigger or whatever. You're not adjusting the scale of one thing to match something else. You're seeing an object in depth, and then you're reaching to that position. We recruited 12 participants for this study, 2 female, 10 male, mean age of about 23 years old. They were compensated $5 for their participation, and they all had normal or corrected to normal vision. So, during the first phase of the experiment, we set the participants in front of a monitor with a wireless mouse. And what they saw, you can see a depiction of it here, there was a static Ebbinghaus configuration. It was either a large annulus configuration or a small annulus configuration with the central disk scaled to a particular degree. And then off to the side, there's a single lone disk. This disk is adjustable. So by scrolling the wheel up and down on the mouse, they can adjust the size of this disk. And their task is to adjust the size of that disk until it matches the size that they see inside the Ebbinghaus configuration. And there were 24 trials. There were 12 large annulus configurations and 12 small annulus configurations. The reference disk size ranged from 3/4 of a degree up to 3 3/4 of a degree of visual angle. Viewing distance was controlled from the monitor, so everyone saw the same visual angle stimuli. And after this phase is when we progressed onto the BlindReaching task. So what we found in the size matching task was, well, one, we had to throw out one subject's worth of data because a data collection error occurred and part of the data set was lost. So 11 participants were analyzed for this. But as you can see in the plot here, there was a rather large difference in size estimations between the large annulus and small annulus configurations. The large annulus resulted in a 4.04% underestimation of the size of the target. So the central disk appeared to be smaller than it was in reality. And for the small annulus configuration, there was a positive 5.81% difference in size, meaning the central disk appeared larger than it actually was in reality. So the difference between these guys is actually pretty strong. We have a p of less than 0.001. But, looking at this plot here, it's kind of obvious that that's the case. However, we wanted to make sure that the magnitude of the effects for the configurations we chose were somewhat comparable. So we looked at the absolute error in judgments between the large and small annulus conditions, and they did not significantly differ. So this gives us some confidence that the magnitude of the illusion that we're seeing for both the large and small annulus configurations were about the same. So we use these same configurations in the virtual world. So move on to the BlindReaching task. So Ebbinghaus is a relative size illusion, and my video is covering up part of what you need to see here. So I'm going to scoot me down to the bottom corner for a little bit. There we go. And so here's a view of what the observers were seeing. They were in a sparsely populated, in terms of furniture and such, model of our lab. And a disc 10 centimeters wide was placed at eye height at one of 5 distances away from them. At the beginning of the experiment, their maximum arm reach was measured. We placed the stimulus object at either 30, 45, 60, 75, or 90% of the maximum arm's reach. And the whole point of this was to establish a size-depth relationship. So this is our calibration phase. They're calibrating their reach to this object. And so they can't see their hand, but there's a red sphere co-located with their controller. And their task is to just touch the disc in depth with the red sphere. And they do this 20 times. Each of the distances were repeated 4 times. So once we finished the calibration task, we then moved on to the BlindReaching task itself. We had 2 viewing conditions. They viewed half of the trials stereoscopically, and they viewed half the trials monoscopically. And this was an attempt for us to sort of tease out whether or not stereoscopic cues, which are quite strong in terms of relating depth information and size information, might have played a role in some of those real-world studies. We tested 3 disc configurations, a large annulus, a small annulus, and no annulus. The no annulus served as our control condition. And we tested the same 5 distances that we did during calibration, 30 to 90% of arm's reach. Each of these combinations were repeated 3 times for a total of 90 trials. We blocked the trials by stereo and mono. So all of the stereo trials occurred together and all of the mono trials occurred together. And half of our participants saw the stereo trials first, and half of our participants saw the mono trials first. Everything else was counterbalanced with a restricted random shuffle, such that whatever combination of depth and annulus configuration you're seeing now, you would see any of the other ones randomly selected next, but you would never see the one that you currently saw in the following trial, so we didn't repeat configurations back to back. So here's a screenshot of what the participants actually saw. This is our lab, and here is the small annulus configuration. And what we found after they completed their trials was this right here. So interestingly enough, there was a very strong effect of annulus size on reach depth for the small annulus configuration, but not for the large annulus configuration. So this is really interesting because we both are and aren't seeing an effect of the Ebbinghaus illusion on depth judgments, but it seems to be contingent on the annulus type that you're testing, which is really fascinating. Another really interesting thing here is the small annulus condition, the condition where the central disk should be overestimated in size, which would be equivalent to it appearing closer to the observer. We saw an underestimation of almost 12%. We were expecting to see an underestimation of close to 5%, which would be in line with the relative size changes that have previously been observed, and also observed in our real world. But instead, we find more than double that, and that's really fascinating. For the large annulus condition, it essentially didn't differ from the control condition. There's effectively no difference between them. It was a very slight overestimation of about 1.5%, slightly more than that. In doing this analysis, we actually grouped the stereo and mono together. We pooled that data because there was no significant difference between them. Quite strongly, no difference. But annulus configurations, as you can see from the plot, were actually quite strong. We had a P of 0.002 on our analysis of variance. We also recorded response time. Now, response time is interesting because it can be used as an implicit measure of how difficult a task is to complete. And what we found is that both the large and small annulus conditions took longer to execute than the control. Now, sort of an off-the-cuff cavalier thing one might say is, well, that's obvious. There was more stuff to look at, more things to process, so it would take longer for them to execute the task. Well, that's not necessarily the case. Most response time and stimulus size studies out there actually indicate the opposite. The larger a stimulus is, the quicker you should respond to it. And we see the opposite here, which implies that the observers are crunching away on this information longer and harder, even if there wasn't a significant change in the depth judgments between the large and control. This could imply that the illusion was actually in play for both the large and small annulus conditions, but the conflict was resolved for some reason more easily for the large annulus configuration. That's just speculation. More work is actually needed to understand if that's the case. So we're running out of time now, so I'm going to wrap this up. So one of the limitations is that we didn't do the size matching task in the virtual world. We only did it in the real world. And we did this, we felt it was necessary to do it in the real world to establish comparability with the prior work. However, a stronger case would have been made if we had done both the real and virtual size matching. Of course, it'd been better if we had more subjects, but we worked with what we had. But we definitely, one of the cool things is we definitely see here that there is an effect of the illusion on action-based tasks, but also a lack in some cases. So this could be a possible explanation for some of the mixed results people have seen in the past. It could be that the stimulus configuration being used is a determining factor. So we're going to wrap it up right there because I am completely out of time. Thank you very much.